Okay, molecules. First question. Explain why the mass number of oxygen is 16. Okay, so oxygen is 16.8. The mass number is the big number at the top. The atomic number or proton number is the smaller number at the bottom. Okay, why is the mass number 16? Well, that's because the number of protons plus the number of neutrons is 16. But be more specific than that. You know how picky examiners are looking at the mark scheme. They've given you oxygen as an example. So say that oxygen, say how many protons it has and how many neutrons it has. That's the number of protons and neutrons, and that's the number of protons. Therefore, the number of neutrons is that minus that. So say that oxygen has 8 neutrons and it also has 8 protons. Okay? That's why the mass number is 16. Don't just say that the number of protons and neutrons is 16. It's not enough. Talk about this specific example they've asked you about. In the case of oxygen, it's got 16 minus 8, which is 8 neutrons, and it's got 8 protons. Okay. Explain why carbon-12 and carbon-14 are isotopes of carbon. Okay, so we've got carbon-12 and carbon-14. They're both carbon because they've both got 6 protons. That's what makes an element an element. It's defined by the number of protons. They've both got different numbers of neutrons, but because they've both got 6 protons, they're both carbon. So you need to know, well, let's just go over what the definition of an isotope is. Isotopes of an element have the same number of protons, but different numbers of neutrons. So that's why these are 2 different isotopes. Same number of protons, 6, different numbers of neutrons. Now remember, the mass number is number of protons and neutrons. So this one has got 12 minus 6. This one's got 6 neutrons. Okay. This one has 14 minus 6. So this one has 8 neutrons. Okay. What was the question again? Explain why they're isotopes of carbon. Okay. So you've got to extract 3 marks out of this. So say that they've got same number of protons. Okay. Say that carbon-12 has 6 neutrons, and say that carbon-14 has 8 neutrons. That will get you the 3 marks. Okay. Next question. Complete the outer shell of water. Okay, where should we do this? Let's do it over here. Right, they've given you oxygen like that. They've put the hydrogen there and the other hydrogen there. Okay, that's what you're handed, and you have to complete the outer shell. It's a dot and cross diagram. So, hydrogen is 1, 1. So, a hydrogen atom provides 1 electron. The reason you know this is that a hydrogen atom has 1 proton and neutron and 1 proton. So it's got 1 minus 1, so it's got 0 neutrons. A hydrogen atom by itself is just 1 proton with 1, let's do it as a cross, 1 electron. Proton has a positive charge, electron has a negative charge. So you'd never get isolated, neutrally charged hydrogen atoms in nature, okay? You never see a hydrogen atom like that floating around, okay? You only ever see a hydrogen molecule, which is one hydrogen atom bonded to another, can also be written as H2, or you might see H plus floating around. H plus is that with the electron removed. So H plus is the same as just a proton. Okay, if you take the electron away from that hydrogen atom, you're left with just the proton. Okay. The reason I've drawn this, again, I want to stress, you never see that by itself in nature, is to show you that a neutrally charged hydrogen atom, were it to exist by itself, provides one electron, okay? And therefore we know that this hydrogen provides one electron. So we're going to draw the electron as a cross, and it's on this hydrogen's outer shell, okay? And the same for the other one. So each hydrogen provides one electron. Right, let's look at a single atom of oxygen by itself. Oxygen is 16.8. So therefore, a neutrally charged, that means same number of protons and neutrons, atom, not molecule, atom of oxygen by itself will have 8 electrons in total. So, let's draw the electrons provided by that single oxygen atom. Okay? The shells fill up in the order 2, 8, 8, 2. So there's the oxygen nucleus. I'm just going to write it as a letter O, okay? The first shell has a maximum of 2 electrons in it. Okay? We've got a total of 8 electrons, so that's 6 left. So therefore it's going to be 6, 2, 3, 4, 5, 6 in the outer shell of the oxygen atom, provided by this oxygen atom. Okay? So therefore there's going to be 6 in this outer shell. Now, because there's 1 provided by the hydrogen, we can put 1 there. And there. And that's 2 of the 6. So the other 4 are going to go here. I'm going to draw them in pairs because they tend to go in pairs on the outside of the atom. But it doesn't matter if you draw all 4 evenly spaced. Okay, now these 2 electrons, one provided by the oxygen and one provided by the hydrogen, that's a covalent bond. Okay, a single covalent bond. So this water molecule can also be drawn like this. Okay, it's a water molecule, it's H2O. A single line like that from the oxygen to the hydrogen is a single covalent bond. And this is that in just more detail, showing the individual electrons. 2 electrons constitutes a single covalent bond. These 2 atoms, the oxygen atom and the hydrogen atom, are sharing these 2 electrons, and that's what the covalent bond is. Okay, so I've gone into that in some detail, but I wanted you to know where the 6 electrons come from. 6 provided by the oxygen in the outer shell. In this question, you're not asked to draw the inner shell. Okay, there's 6 in the outer shell and there's 1 in the outer shell of the hydrogen. So you'll notice that the oxygen atom has, because it's, if you like, borrowing or sharing this hydrogen's electron and also this hydrogen's electron, you'll notice there are now 8 electrons in the outer shell of oxygen. And when its outer shell is full, which it is now that it's borrowing the 2 from the hydrogens, it's stable and happy, if you like. And that's why the water molecule is a stable molecule. It's why it takes this form. And the same with the hydrogens. Because this hydrogen is borrowing this electron from the oxygen, it has 2 electrons in its outer shell. So its outer shell, the first one, is full, so it's stable and happy. And same with that hydrogen. Okay, let's move on. Name the type of bonding in a molecule of water. I've already told you, it's covalent. Okay? These 2 electrons being shared by the 2 atoms forms a single covalent bond. When the outer shells overlap the way they do here, then you have covalent bonding. You can also have ionic bonding. This isn't part of this question, but I want to tell you anyway. It's important you know this. Let's look at sodium chloride, for example. If we have a sodium chloride molecule, the atom of sodium here and the atom of chlorine here, I'm only going to draw the outer shells like this. We won't worry about the inner shell. Okay? Sodium has 8 electrons in its outer shell. Okay, it's the second one, it's this one. Okay? Because it's lost one of them to the chlorine. One of the electrons that originally belonged to the sodium has been borrowed by the chlorine. See, the chlorine itself, which I'm going to draw their electrons as dots, only provides 7 electrons in its outer shell. Okay? Now, you'll notice that the outer shells, I've drawn them not overlapping, and that's really important. When they don't overlap, you have ionic bonding. Okay? It's ionic because these 2 are ions, and you must not forget when you draw ionic bonding diagrams to put some big brackets in like this and show the charge. Chlorine has a negative charge and sodium has an overall positive charge. Don't forget that. So that's how you draw ionic bonding, and that's how you draw covalent bonding. Covalent, overlapping; ionic, not overlapping. Okay. Why does pure water not conduct electricity? Okay. Just got to remember this. Pure water doesn't conduct electricity because there are no free ions in pure water. You've just got water molecules, and there's no way that charge can be carried through the water because, just remember the phrase, there are no free ions, or no ions free to move in pure water. Or if you like, there are no charge carriers free to move through the water. This is, again, a bit of an extension to the question, but you need to know it. If you put salt, that's sodium chloride, okay, in water, so now you've got a solution of sodium chloride, NaCl, and water, so that and that's also known as brine, or salt water. That can conduct electricity because you've introduced charge carriers to the water. When you dissolve salt in water, the sodium and the chlorine, they dissociate and they float around in the water independently. And so in brine, salt water, you do have free ions which can carry a charge and conduct a charge, but in pure water you don't. Okay. Next, let's stand here. How does the size of a nanoparticle compare with the size of an atom? 1 mark. Well, you've just got to remember that nanoparticles are bigger than atoms. That gets you the mark. I know nanoparticles, the word nanoparticle, wow, it must be really small. It is really small, but atoms are much smaller still. Okay, to give you an idea of the size of a nanoparticle, they vary in size, but generally a few hundred atoms across. So relative to an atom, okay, so one atom, say, there's a hydrogen atom, a nanoparticle is hundreds of times bigger. So it's therefore nanoparticles are also bigger than molecules. There's a water molecule, but they're still really small. Okay. Suggest one reason why 1 gram of cobalt oxide nanoparticles is a better catalyst than 1 gram of cobalt oxide powder. Well, this always comes up in chemistry. The answer, it has a larger surface area. Very common exam question. You can often say, oh, surface area for a lot of catalyst questions and get a mark. But 1 gram of nanoparticles has a much larger surface area than 1 gram of powder, because to the human eye, the powder is still very fine. Yes, it's made up of lots of tiny little lumps of the material, but those little lumps that to our human eye are very fine, they're still much bigger than nanoparticles. And nanoparticles in turn are much bigger than atoms. So 1 gram, that means the same amount by mass, okay, of nanoparticles compared to 1 gram by mass of just the powder. The nanoparticles will have a much larger surface area because the individual particles they're made up of are much smaller. And whenever you have a substance that's the same amount by mass as another substance, and this substance is made up of much smaller particles, the surface area is larger. So same amount by mass, smaller particles means larger surface area. Okay, so to get the answer, the reason is, I can't remember if I said it or not, just to be sure, the nanoparticles have a larger surface area. There we go, finished.